Basically, for what we would call modern electromagnetic theory, we can start with the work of James Clerk Maxwell. That's usually a starting point most people take because he put it together based on Faraday's work. Faraday was a great experimenter and did a great number of experiments which showed very nice things. And Faraday had some concepts of his own which he advanced, but he did not mathematize it. He didn't make math models of it. Maxwell, for example, even made a statement that when he first started studying that, he made a vow not to look at anybody else's work until he finished capturing Faraday's work mathematically. So he set out to deliberately mathematize what Faraday had discovered working on the bench. And his actual theory, which is in a paper published in 1865, was orally delivered in 1864. His actual theory is 20 equations in 20 unknowns, quaternion and quaternion-like equations. The quaternion differs, understand at this time there were no vectors. Vector and tensor analysis was not yet born. And so what we had is various kinds of algebras and things like that. But quaternions had been created by Hamilton. And they were what we call a higher group symmetry. They captured lots of operations, intricate operations that today's theory does not capture at all. To give you an example, there's always a great dispute about Nikola Tesla's work. And most of the conventionally trained scientists assume that they know and understand everything Tesla did. They do not. One of the really fine electrodynamicists and electrical physicists we have in this country is a man named Terry Barrett. Barrett took a look at Tesla's actual patents, but he looked at them in quaternion algebra, the same kind of thing that Maxwell was originally using in his original theory. And surprisingly, there were many operations going on in these circuits that could be seen with quaternion electrodynamics, could not be seen with the best tensor analysis you could do. So Barrett published a paper on it to show what was actually going on in those circuits. He also saw some ways to improve what Tesla had been doing, and he filed and obtained 2 patents which are still used in communication industry and things like ultra-wideband radar. So it does work. But my point is that we started off with this better model, but it was much more complicated mathematics. Now in those days, the fashion was to call what we today would call electrical engineer, call them electricians. And most of them were more like electricians than what we would consider an electrical engineer. And for example, people like Heaviside looking at that said, you know, these poor electricians, they'll never learn these silly quaternions. That's far too complicated. This has got to be made simpler. He wasn't the only one that took that view, but he was the major one that played a major role in cutting down those equations and making them much easier and much simpler, and therefore losing lots of operations you can do. But a quaternion has one peculiar thing. It takes a vector, what we today will call a vector component, one that has direction as well as magnitude, and it sticks on the component that doesn't have any direction, just has magnitude. And people like Heaviside, who was totally self-taught, never went to university at all, but brilliant man, brilliant. We're not knocking Heaviside at all. Heaviside said, that's mixing apples and oranges, so let's chop off that part that's not got a direction. And that's the way vectors were born. Heaviside and Hertz and primarily an American also named Gibbs basically taught our scientists vector analysis. They created vector algebra, vector analysis. And they did it in refining and condensing and chopping up Maxwell's equations, Maxwell's original theory. They reduced it to a much smaller subset of the theory.
Can you paraphrase some of Maxwell's work narrowing it for our purposes in terms of how it is applied to the energy from the vacuum work that we'll be addressing overall.
Yes, Maxwell had one vision, and what he thought was the primary reality in electrodynamics was the potentials. Heaviside and the others thought the potentials were mysticism. They weren't even real. If it was not force, it had no reality in the physical world. It's all right. Most scientists thought that. So he thought that these were just mathematical niceties that Maxwell played around with. So one of his real jobs, he said, these things ought to be murdered from the theory. That was one statement that he made. One of his primary reasons was to get rid of the potentials, and he got rid of all of them but two.
Heaviside.
Heaviside did, and so did Hertz doing the same thing, and so did Gibbs doing the same thing in forming vector algebra and vector electromagnetics. The equations, for example, that are taught today at universities, Maxwell's equations, are not Maxwell's equations at all. They are Heaviside's truncated equations. But anyway, Heaviside took the view that, these potentials are mystical, we've got to murder them from the theory, and we've got to get rid of them, and so they did. Oddly, in today's modern physics, we know the potentials are what's real, and the force field is an effect made in matter after something much more fundamental interacts with the matter. It hasn't made it into electrical engineering yet in 50 years since we've known it. Maybe it will one of these days migrate from the physics department across the campus to the building where the electrical engineering department is and get them to change the thing. When you assume force fields in space, you assume a material ether, which everybody did when they first started the theory. Even Maxwell believed in a material ether.
How would you define that?
Material ether is that there's a thin gas, a thin material gas filling all space. And there's not a point in the universe where mass is absent. That's called the luminiferous ether. It was destroyed in 1887 by the Michelson-Morley experiments. All the electrical equations all assumed this material ether, and still do. They never changed a single equation. What they did one day is they got up and announced, well, there's no material ether, so we're not using one. And they kept right on with the same equations, all assuming the material ether. What you do in a case like that, it does not allow you to engineer force. You have to start with force, and you're automatically into what we call entropic engineering. You've beaten nature in a wrestling match with nature. You're fighting forces all the time. You don't have to do it that way. If you just flow the energy in freely and transfer it and shape and form the energy as you wish, and then interact that with matter, you form powerful forces without ever having to wrestle nature. And that's the way to do engineering. That's negative entropy engineering, which will be the engineering of the future if we ever get it born. Anyway, Maxwell's equations still had a much greater variety of things that you can do electromagnetically than our people can do today at the universities. This got truncated after his death. Maxwell died in 1879 of stomach cancer. And the Heaviside work and the other works only got going in the 1880s. Beginning of the 1880s is when they did most of their work. So after his death, his equations were severely truncated. Now I'm going to say something in Heaviside's defense. He was probably right when he said, our poor electricians will never be able to understand and grasp these quaternions. We've got to have something simpler. He was probably right on the mark. Because if they had not simplified it and oversimplified it, they would not have ever got it off the ground and running to make practical things. That is true.
Yeah. We had a problem in those days with both concept and calculation.
That's correct. So anyway, we get after Maxwell's death, we have the tremendous work of Heaviside. Gibbs' work gave the mathematics in circulated papers, which were widely circulated. And Hertz, who had a short life, but as you know, Hertz proved experimentally, I think some 9 years after Maxwell's death, that the equations Maxwell had said predicted waves actually did produce waves. The theory produced the waves, and he proved it experimentally. And at that time, after we finally had experimental demonstration of these waves, then science began to pay attention to Maxwell's theory, to the theory as it was then existing more in truncated form. Okay, we get along up to towards the end of that century. When we get up towards 1900, another scientist of great impact on electromagnetics entered the picture, named Lorenz.
Before we go to Lorenz, I'm sorry to interrupt. What is it? I still don't get, and maybe I missed something. What is it about Maxwell's equations that is directly applicable now to energy from the vacuum?
Okay. Maxwell's equations do apply to energy from the vacuum because they apply to systems which are not, to be technical, are not yet symmetrically regauged. Now, what the devil does that mean? When you say regauge a system, you change its potential energy. You can change the potential energy of any system free as anywhere you wish, anytime you wish, and every electrodynamicist already assumes that and uses it, and so do the gauge field theorists. The gauge freedom axiom guarantees you don't have to pay work to change the energy of a system. You can have all the energy in the system you want to pour in there. You do not have to do work just to get the energy there.
I want you to define energy and potential.
Okay, there are two things that have no definition, but we'll define it.
Well, that's why I asked you.
Gotcha.
Anyway, if we change the energy density of space-time, you see, we make a curvature of space-time when we do. Now, at the time we're talking about, relativity hasn't been born yet, neither special nor general. So curvature of space-time is not a concept that's being used in science at all at the day we're talking about. They started with a model that they assumed never had a curvature of space-time and never had any change in the vacuum flux because there was no such thing known as a vacuum flux. Most of the particle physics for that had never been born. So we're in a time when, completely innocently, a very restricted theory which says that, you know, space-time never curves and that curvature then never interacts back on our system, which it does. And the vacuum never changes, it's just empty space, it never changes and doesn't interact back on our system, which it does. We know today. It does violently, but that's totally ignored in that theory. So even in Maxwell's theory, that was not known, so it's not in the equations. But if you take the equations, they still allow you to have extra energy coming in from outside and model this situation. Because now what you will have, it'll create a free field, not just a potential. You can do that for free. But the difference between that potential and some other potential at a different potential in the circuit gives you a field that's free because the potential to make that difference was free. Once you have that field, you have a free force field in that system, which we would call forward EMF, which will now push the electrons through the load and do some free power in the load till it dissipates that extra energy that we moved in for free. In other words, if we have an asymmetric means the fields didn't stay the same. You let the extra field get born for free. Didn't cost you anything. You made some force for free. You got it free from nature. Nature said, oh, you did fine. You moved into energy and then you let me give you the force for free. And then this force can do work for you for free till it exhausts the energy that was extra. But you see, the equations, when you do that, when you have what we call asymmetry or broken symmetry in them, they're not symmetrical. And everybody loved symmetry. It was beautiful. They wanted to see the two sides of the human face just look like mirror images of each other. They didn't want to see one different from the other. Oh, that was ugly. So the mathematicians, chasing beauty, abhorred broken symmetry. They hated it. And it was nothing in the world but admiring the beauty of the equations when they were symmetrical. So when Lorenz came along, Lorenz, he regauged the equations symmetrically. Okay, what does that do? What did it do that it had to do with energy systems? Well, let's reason together. If my system is allowed by the equations to freely receive energy from outside that doesn't cost me anything, and is allowed to freely use that energy to power the load, can I not get some free energy from whatever the source is providing all that from outside, which today we know is curved space-time and the active vacuum, the environment? Yes, we could do that with those original equations, but if we make them symmetrical, we can't do that. Anything that flows in flows right back out. I don't have any extra thing. Or it flows in and its opposite flows in, and the two do nothing but stress the system. They won't do any work in the load. In other words, there will be no net field. There'll be two opposite and equal fields that are free.
That's symmetrical.
That's symmetrical.
Right.
That's what Lorenz did. He made the theory symmetrical because those equations are much easier to solve. They didn't have computers. Numerical methods were a bear, and they still are if you have to do them longhand. Today, they're a piece of cake for a bright young grad student. He simply takes a Mathematica or something, slaps it in here, and the computer grinds out the answer any which way he wants it. That didn't exist back then. So there was a great need and urgency to make these equations easier to solve. So Lorenz made another change. It made them a lot easier to solve. And guess what he did? He threw out all the over-unity systems powered from the vacuum. In one stroke of the pen, to make the equations more beautiful and easier to solve, completely unwittingly, he threw out all the future systems that could have been built taking energy from the active vacuum or from curved space-time or both. He discarded them with one stroke of the pen. And today, in every university, Maxwell's equations, that is, the Heaviside equations, have this extra added attraction of being Lorentz regauged, symmetrically regauged. Now, what does that do in a circuit? In a circuit, you've said, this circuit is going to have a forward EMF, that's that force, you see, and this back EMF are going to be equal. We're going to guarantee that circuit is equal in the forces. So there's no free force around there anywhere for you to use for free.
And yet Maxwell's original equations...
Maxwell's original equations allowed that.
Is this the area where they said it had no physical...
significance, no.
Yeah, no physical significance.
The extra wind was of no...
Yes, the basis for being so shy on the potentials was that, people thought they had no physical significance. They honestly believed that. It's only since quantum mechanics got born and so forth that we've gone back and found out that potentials are what's primary, and the force fields are effects made by the interactions of something that's a specially shaped potential that interacts with matter. The force field is not primary at all, but you see, still in our text, it's treated as the primary thing, particularly in electrodynamics and electrical engineering. But after this Lorentz regauging, you still had a problem. The problem is, if you built your circuit physically where it would comply with that equation, that symmetrically regauged equation, then that circuit would not go over unity. But suppose you didn't build your circuit that way. Then, foolish person that you are, your circuit will act up. It will do all kinds of weird things. And it may, in fact, put out more energy than you're putting in. It's taking the energy right out of the vacuum. It has a net extra force. It will do net extra work for free for you in the load. That would be nice, but it's ugly. It's not symmetrical, so it has to be destroyed. Well, they did destroy it, and what you have to ensure, this is totally unintentional now, unwitting. They all went to the simplest circuit that eliminated all those crazy problems most of the time. And guess what that is? A well-grounded, closed current loop circuit with the external source wired into the circuit as a load. Now let's reason together. Let's go back to the generator. I have a source of energy, and let's don't worry about the source right now. Coming out of the terminals of this generator, there's a flow of energy coming out of here. Okay. The voltage from the top to the bottom of the generator is a certain voltage. The voltage all the way around through the external circuit to that same point, given perfect conductors and all that, is in fact the same voltage. The field, the electric field all the way around through that whole circuit back to that point is exactly the opposite of the electric field that we call the back EMF between the terminals. That silly circuit has made the forward EMF and the back EMF, that is the two fields that we get for free when we introduce potential to the circuit and change its energy. It's made the two fields that we get equal and opposite. It self-enforces Lorentz symmetrical regauging, thereby guaranteeing that that silly circuit will never produce more energy out in the load than you got to put in the shaft of your generator.
So if you build a circuit that follows different rules, it has been called unexplained.
That's correct.
But in fact, it was explained
That's correct.
earlier in time.
If you want to work in this field, it's not yet a field, the field of taking energy from the vacuum and getting a net force field in your circuit to give you some free work in your load, if you want to follow this field and do well, your first requirement is to violate the standard closed current loop circuit. Until you do that, you cannot ever go over unity. Now, isn't it interesting that 85 or 90% of the people working in the so-called over unity field will come in and guess what? They will wire up a closed current loop circuit. They will guarantee self-enforced symmetrical regauging and their system will never work. And you can hand them an operating system that isn't wired that way, and they will say, this foolish fellow doesn't even know how to ground a system or how to build a proper closed current loop circuit. And so they will correct it. And that system will no longer perform because it's now a symmetrically regauged system. It will no longer give you more energy out than you're putting in. Regardless of how much free energy it takes in, it will use half of it to destroy the source. The other half, it'll spill some in the losses in the system. You'll get less than half out in the load. If you had a 100% efficient generator, didn't lose anything in the generator, no such generator exists, but if you did have one, you would have to put back in shaft horsepower exactly as much energy as was used to destroy the dipolarity of the generator. So you would have to put in that half that was used to destroy the generator. If it's less efficient than 100%, you have to put in more. That's automatically more than you're getting out in the load. So that circuit will never allow you to go over unity. You will always have less going out in the load than you got to put into the shaft of the generator.
So
That's not the way to build a power system.
And it's not also dependent upon, you have mentioned things like thin film, newer technology, but it's not really the newness of the technology. You could use traditional inductors and capacitors to create an over unity condition.
The old guys did. They didn't even have semiconductors. They didn't have all these other things. Tesla didn't have any of that.
Right.
He made over unity systems. Right. Stubblefield certainly didn't have any of that. He made over unity systems. And the point is to break up the symmetry. Because today we know in modern physics, once we say broken symmetry, Lee says it very gently, Noblest Lee. He says, something virtual has become observable. In other words, you get some virtual energy out of the vacuum and you convert it and change it and compress it into observable, real energy you can use.
Right. But in the overall schema of nature, this symmetrical regauging only takes place artificially in the electrodynamic world, doesn't it?
That's correct.
Yeah.
Nature is full of systems that are asymmetric. We owe our life to it. The sun radiates energy, which makes the biosphere here on Earth possible.
Yeah.
There's continuous input of energy. If you were to take that away, so for example, vanish the sun, just black it out, everything here on this Earth would die. It depends on a steady input of free energy that we don't pay for. You don't have to pay for the sun. If you did, we'd be hard put to manage it. But everything that we know of depends on this steady input of energy. Nature freely exchanges energy. Every energy transfer costs nothing. It's not work. Work rigorously is when you change the form of some energy into a different form. Then you do work. If you just want to change the magnitude of some energy and you flow in the energy in the same form, costs you nothing except you got to have a line to flow it in on. But you don't pay for the energy to build up any amount you wish. Energy always occurs in a flow. That was the beauty of Whittaker's work in 1903 and 1904. He took what we call a potential and what we call fields and things like that and decomposed them and showed they are made of energy flows. And that's rigorous work. His second paper started a whole subject called superpotential theory. Unfortunately, they continued to ignore his first paper, which gave them an internal electrodynamics much more fundamental than the external stuff we use. So the internal structuring we just continue to ignore. We only look at the brute force fields and the brute force potentials.
Was it Whittaker that initiated the energy flow through space theory?
No. That was originated by two men. Energy flow through space did not exist in Maxwell's day, before Maxwell's death. The concept of energy flow through circuits, through space, all this stuff, originated with two fellows, one John Poynting and the other Oliver Heaviside. Now Poynting is an academician, PhD, well-known scholar, and so forth. Heaviside is publishing in more obscure publications than the Proceedings of the Royal Society. He later got some in there. But most of his publications, lots of them, were in a thing called The Electrician, which was something like Scientific American today would be. That's a close parallel to what it was. And Heaviside was always publishing things that had direct practical utility to how to wire a transformer, how to fix transformers on lines and make everything efficient and so forth. So a lot of his work had very practical applications. Some of it was also very theoretical, like the Heaviside functions he created. The mathematicians hated him. They criticized him and attacked him and said, you know, this dirty guy doesn't even know how to do good mathematics. And later, a real famous mathematician came in and said, he does too, because that's beautiful stuff if you understand this part. And finally they said, oh, okay, we'll take it. Nobody ever apologized to old Heaviside. But the point is, energy flow got born in the 1880s by Poynting and by Heaviside. Poynting never considered anything but the amount of energy that enters the wire from the circuit from outside. See, the energy flow is really on the outside of the wire. It doesn't flow through the wire at all. But a little bit of it gets diverged, we would say, into the wire. And that little bit forms all the fields inside the wire that push the electrons through the load and power the load. So he only considered that vertical component that enters the wire. He considered that the flow of the energy. Well, you see, that's not the flow of the energy along the circuit. He got it wrong by 90 degrees. Heaviside corrected him, and Heaviside showed that you had this flow going along parallel, and only a tiny component gets diverted in there. Well, this was an embarrassment. First, they had to buy the Heaviside stuff was accurate, so they had to buy that. But it had a problem. Boy, did it have a problem, and it's still got a problem today. The amount of the energy flow that's going outside the wire, coming out of the terminals of the generator, that's diverted into the circuit and powers the circuit is only a tiny bit of the actual energy flow going on. Let's use a number. I looked at a couple of circuits, and the best that I could estimate, very simple ones, the best that I could estimate it, the rest of the energy remaining after the part gets diverged, the part that doesn't get diverged, that's divergence free, is about 10 trillion times as much as gets diverged. What if we said, if you don't like the figure 10 trillion, take a billion. It's a large number. What do we make of a generator that we put so much mechanical energy into, and this cotton-picking thing is pouring out 1 billion times as much energy as we put in cranking the shaft? Where does the energy come from? embarrassing because nobody had the foggiest notion, neither Heaviside or anybody else. It was so bad to try to keep from being accused of a dirty old perpetual motion fellow and advocate violating conservation of energy and creating energy. He only spoke obliquely of the directions of the energy flow. But he did get across that the energy flow remaining that didn't get diverted was far larger than the part that goes in our circuits and we use.
And whose formulas were defining this 10 trillion times more energy?
It's never been worked out exactly that I can find. It may be in Heaviside stuff somewhere. I haven't read every paper he wrote. But Heaviside did understand it was enormously bigger than the part that got diverged, because he says so. That tiny amount that gets diverged is responsible for power in the circuit. And he left it at that, so he wouldn't be accused of being an idiot.
But it's in Krauss's, it's memorialized in today's theory, isn't it? I mean, it's a common, that doesn't Krauss's Electrodynamics book go on?
No, he shows the flow outside there, but he doesn't show the Heaviside component. He implies that all that gets diverged. It doesn't. So now we come to Lorenz, the greatest scientist of his day at this time. We're up into Lorenz's day now. Lorenz looks at that. He well understands Heaviside's work. He well understands Poynting's work. But he hasn't got the foggiest notion what on earth could possibly be a source for all that enormous energy that didn't get diverged in the circuit. Since it's divergent free, it means it's in a curl form and it doesn't interact with anything. It goes out and normally doesn't interact with you, with the environment, or anything very much at all. Just usually gets just wasted. But it's there. So a problem that Lorenz was facing was, we have this irresolvable problem. What do you do with it? First of all, even the great Lorenz, if he had said publicly and clearly, there is enormous energy flowing from every power source, far, far greater than we ever catch in a circuit and use, including, even billions of times greater, why, he would have been tarred and feathered and ridden out of town on a rail, so to speak, by the scientific community, as advocating creation of energy from nothing. Well, if you can't solve the problem, scientifically you can do another thing. You can eliminate the problem. Get rid of it, so it's not bothering you anymore or anybody else. But to get rid of it, you've got to have a very smooth, elegant statement that just slides so pretty, just like silk candy. It slides right through the mind and doesn't stir anything. Everybody just accepts it right on. So what Lorenz did is he originated a clever little integration trick. He visualized around any point in the circuit, any point you want to take, you must visualize a closed surface around it. Now, understand energy flow is going in this surface, coming out the other surface. A little tiny bit of it is being diverged inside here into the circuit. So a little bit less is coming out than is going in. But if you integrate the energy flow vector itself that represents energy flow around that closed loop circuit, what it will neatly do, the parts that go through and don't get diverged, it'll subtract them. One's positive, let's say, going in, is negative going out. They go to zero. It only leaves a little component that goes in and gets diverged into the circuit. And what you do is you say a very clever statement that Lorenz came up and says, this other component, this Heaviside component, has no physical significance because it doesn't do anything. It won't interact with anything, so it has no physical significance. Doesn't that sound smooth? So it's exactly what he taught everybody to do, and once you did that, the problem went away. All you have is the amount of energy goes in the circuit. Half of that now goes back to kill your source. Less than half is going to get in your load. Now you're down home free with an under-unity circuit. Everybody's happy. And meanwhile, every generator you ever built and every battery that you ever got out of the battery store puts out enough energy flow to power the whole continental United States. Could you catch it and use it? But you're not permitted to know that anymore. And if you find out about it, you will be laughed at and it will be called ludicrous, but it is a fact. Now, can we prove that? Yes, we can. Fortunately, we can. The only way that it stays non-divergent is to stay in a flat space-time condition, or reasonably so. If I have something that will curve space-time a little bit, all of a sudden the divergence of a curl is not zero. Mathematically, you just blew vector analysis out the window, because you got to go to tensors once you get curvature space-time. You can't stay down in those vectors in flat space-time. You got to allow for the curved space-time. You got to bring in general relativity. And what had been a zero mathematical operation is no longer zero. This means that you can catch some of that extra energy, at least a little bit of it, and you can use it. And there's an area in physics which does it, and they never discuss thermodynamics. It's called negative resonance absorption of the medium. A little charge exposed to potential or field or energy input to it has a certain, what we call, reaction cross-section. Look at it like a rock in a river. It'll divert so much of the stream around it. But if the rock is not fixed, if it goes into violent oscillation, it'll disturb lots more water around it. It'll collect lots more energy. So when the particle, a charged particle, is chosen, which at the frequency of the energy I'm feeding into it, it goes into self-resonance. It will collect in the ultraviolet or the infrared, if I arrange things correctly, 18 times as much energy as I calculate I'm putting in for any collection on a static rock, which is the way electrodynamics is written in the model, for static matter. It will collect 18 times as much energy that you don't think you put in, and your numbers that you crank out of the Poynting energy flow say was never put into the circuit. And you'll have articles that say, how can a particle absorb more than the energy impinging on it? And blah, 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 blah about how it does that. Basically, it takes the energy out of the vacuum, because the other energy was there in the vacuum all the time in that special Heaviside form. What you really did was prove Heaviside was right. And there is enormous energy in the Heaviside component for us to get and use if we will turn loose the sharp young grad students and the sharp young postdocs and fund them and let them go get it. Department of Energy, are you listening? One generator, one massive plant that you build and put in or administer, could power the entire United States if you would go catch the energy you're wasting. You don't have to destroy the biosphere and burn all the oil and all the coal and all that if you'll do some science that Heaviside did before the turn of the century. And that's a century ago. So over 100 years old we're talking about. It's been ignored. It's time to pay some attention to it. Any way you can catch it. We tried to point out that if you used a Heaviside processor and you didn't get the 18, you only got 10, let's say, because of a lot of losses. If you put a thing that would absorb the heat that you make from burning the coal in a standard plant before you get it to the boiler, and let it do a 10-to-1 amplification for you by taking the energy out of the vacuum with that process that's already in physics, you could eliminate 90% of the coal burning right there with one change to your present generators, plants.
Interesting.
Why aren't we looking at things like that? National Science Foundation, you put out a big study in 2000 saying, well, our job is to look at innovative things. Why aren't you doing that? Why are you still talking about how I can burn some coal a little bit cleaner, or how I can burn the oil a little bit more efficiently?
Well, because it was excised from our system, our education.
It's been excised from the system, and therefore it's not a matter of intent. It's unwitting.
Yeah.
It's an unwitting negligence by the whole scientific community. But it's in the literature. It's sitting there waiting anytime anybody wants to pick it up and run with it. I didn't originate it. Heaviside did. And Lorenz couldn't solve the problem, so we got rid of it. And everybody else can't solve the problem either. They don't even want to look at it. They grab what Lorenz did, and they're all taught to do the same integration and use the same set of words. It has no physical significance. We can show you that in Jackson's book and several other books.
Well, it's like you've already said. The particle physicists are not going over walking
That's
across
correct.
the campus to the...
That's right. So we have things sitting in our literature which, if followed up, would solve the energy crisis forever, and could be done fairly quickly, some of them, and nobody is paying any attention.
Well, that's-
It's a problem in our system. It's a problem in our scientific system because don't blame Bush and Cheney. Where do they get their advice? They get it from our scientific community. And our scientists tell them absolutely honestly with everything they know and with their heart in it. Mr. President, Mr. Vice President, you can't do anything else. We don't know anything else you can do.
Well, and their General Electric sponsored funding,
That's correct.
that doesn't hurt their point of view either.
You control, science got controlled, you see, because you control science by controlling its funding and how it's spent. The PhD sitting out here in the local university does not have control of the research he's going to do. Sorry about that. Two things, he has to publish papers and get them published, so he's got to go through peer review. He can't get too innovative or he'll get tarred and feathered. Run out of his position and be lucky if he can work at the local fast food store. He's got a problem that the university is on his back to bring in extra money from outside. If he doesn't, he's not considered worth his salt. At best, they'll park him somewhere teaching sophomore something or a freshman something, and that's it. He's got to have extra funding also to pay his grad students for their doctoral programs and also to his postdocs. So his problem turns down primarily to be, I've got to have extra funding, and the funding comes down in packages with the research already prescribed that you're going to do. Already laid out and told what you're going to do. He has to bid on these packages and he has to win some of them, or pretty soon he's either on his way out or if he's got tenure, he winds up being the sophomore instructor and that's it.
I want to talk a little bit about energy flow through space in a manner that you have before in terms of the pipe and the river and what goes through the pipe and what's flowing around the pipe.
When we talk about energy, we get into, and we talk about it in the fuller sense, not like we're using it presently in electrical engineering, but when we also talk about it in the larger sense, where we bring in the general relativity and we bring in the particle physics. And we look at those interactions, which are always going on, they always generate forces. We've just found how to sweep them out and not have to pay attention to them in normal engineering. But we paid a bit of price for doing that, for making it simpler, because we eliminated our ability to get the energy out for free or almost for free. And so we've had to pollute the biosphere and everything, have ever more energy to burn more coal, burn more oil, whatever. Yeah. We don't have to do it that way at all. We can burn a lot less of all of that stuff, far, far less than what we're doing now, if we would but work the problem. So, but when we get into energy, we find that we have positive energy and negative energy. In a vacuum, since Dirac's theory and modern physics, modern particle physics since then, we understand that the vacuum is full of little virtual particles bubbling everywhere. Incredible energy. You can also represent it as a set of holes that each filled with a, if you don't like the bubbles so much, and each of these holes is filled with its corresponding particle. For example, like an electron. There's a hole here that's exactly will hold an electron, and once a real electron falls in there, the hole is full. The vacuum is what we would call empty space at that time, with the hole filled. Another electron coming in doesn't have a hole to fall into because it's already full. Right. But if you put some energy in here, you can pop this electron out of here and leave the hole. And if you're clever, you can take the electrons that you got for free out of this process, well, for the energy you paid, you can go use them. You can also use these holes, but that's negative energy. Now, the way they use negative energy at present, they assume it's already interacted with mass somewhere, swallowed another electron and left an excess positive charge, which then is a positron, a lattice positron. All the solid state people use lattice positrons. Okay. As long as it has not interacted with matter, the Dirac hole is not a positron. It's a negative energy electron, and it has negative mass. And you can hold it in that state without being filled for a short time, at least in circuits. When you do, acting as a source charge, it's producing at the speed of light negative energy photons, which are establishing negative energy fields and potentials from it. So you can have a flow of negative EM energy along a circuit as opposed to positive energy that we have in our textbooks, if you trick it just right. Okay. what is the useful part of that? Let's talk about the function of a circuit when energy flow is flowing along it. Positive energy is divergent. And remember, pointing only got the diverged part that comes into the circuit. It's the divergent energy. It's always trying to diverge from its line of flow and escape back to the environment. It's trying to get away from where you want it to go. So what we call conductivity, like in a conductor, is the characteristic of that conductor to be a waveguide, to prevent that escape of positive energy and hold it along its path. So if I have perfect conductivity, I don't have any loss. The energy is forced to hold in place and gets across to the other side. I get just as much out as I put in. But normal circuits are not pure conductors. We have impedances. Even in the wire, we have little impedance. So what we have is we have an impedance that is met along the path. An impedance, by definition, is a small reduction, at least some reduction in your conductivity. That is, it reduces the ability of that wire to be a waveguide and hold that energy along it. So some of the energy escapes and leaks off. And we call that losses in the circuits. So for positive energy, I put some in at the beginning. I have my impedances. Certainly if I got a load, I got impedances. But I've got impedances in the way my circuit is made anyway, and I'm losing some all the time. So I'm going to get less out there in that load to power it than I put in. It's the leaky diode, leaky pipe. The pipe carrying the energy to this load leaked all the way, and I didn't get as much over to the load as I put in. Sorry, I'm under unity, particularly since I got it in a closed current loop circuit and I'm killing my power source with the other half all the time. But negative energy is nature's beneficial grant to humankind and to the world. Negative energy works exactly backwards. It's the convergent energy. It's the energy that the environment is always trying to pour into any flow of negative energy going along a conducting path. The environment is trying to put more negative energy in there all the time, free. You don't have to pay a thing for it. It's trying desperately to do that. Conductivity now is still the process of preventing change and of doing that waveguide and preventing any change. So the negative energy flowing, well, the conductivity will not allow any excess energy to flow in there. And so in this pipe, I will now get out a pure conductor. At the other end, I'll get exactly what I put in, just like I did with positive energy. But again, it's not a perfect world, and the circuits are not perfect conductors. There are impedances. But now when I meet an impedance, what it does reduces the conductivity, reduce the wave guiding, which means some excess energy now crowds in here and converges in here, negative energy. Coming past that impedance, I have more than I'm putting in. The next impedance, I get some more. So if I have a series of impedance, by the time I get to the end of the flow, I have enormously more flow than I'm putting in. 10, 15, 20 times more in a common circuit. Maybe 100 if you really do things real fine. So I have lots more negative energy coming out than what I'm putting in on the other side. I didn't create any energy. Nature kindly gave that to me because she said, oh great, you allowed me some impedance where I can give you the energy. And I'm happy to do that. Here it is to you for free. And you say, well, we got to have positive energy to run loads. Well, we do with the way we design them. We could design them to use negative energy, but nobody's ever thought of it. Nobody's ever developed negative energy flows, except one fellow named Bearden. And so nobody has paid any attention to using circuits in the negative energy role rather than a positive energy role.
Well, you had mentioned yesterday that Sweet's circuit had...
Sweet's circuit produced more negative energy than positive by far in his device.
And Gray also.
Gray, splitting the positive, yes, he was dealing with some negative energy. If you really got the kind of motors you're making today, which demand positive energy, all you got to do to convert negative energy to positive energy is invert the terminals of a capacitor and charge it. Negative charges backwards from positive energy. And then take the capacitor, charge real quick by the way, and turn it around and connect it back onto your load, and it'll discharge normal garden variety positive energy and run the load. So it's something that can be done in every circuit.
What's an example of a negative energy generator?
Only something built by Bearden that I know of is doing that right now. The sweet device, its output was more, anytime you have a system taking energy from the vacuum and producing more out than in, obviously you have to involve some negative energy, or you wouldn't get out more than you put in. You've gone into the use of some fraction of your system in the negative energy mode, where you understand it or not. But since we don't build over unity systems, we don't have any phenomenology in our textbooks.
So in other words, in something like Sweet's device, he had to have been creating those holes
Yes.
in order to, which is the definition.
But you see, you create them normally. Anytime you pulse things or make gradients or anything, you create holes all the time in every circuit. It's churning around. It's never just a steady vacuum that's going on. You're interacting on that vacuum, and it's interacting back on you in that circuit all the time. We just don't allow for it in normal electrical engineering. But particle physics can tell you that's happening. It's already in the physics book. It's just not over in the electrical engineering book.
How is Wu's work influential in this?
Well, the Wu's work had to do with Li and Yang's prediction, and starting particularly in 1956 and early 57, of broken symmetry. Remember, everybody was worshiping symmetry. And all of a sudden, broken symmetry comes out of Li and Yang as being a major thing. You cannot avoid it. Well, this was overwhelming. This was such a revolution that, were it true, it would revolutionize all of physics, which it did. But what I'm saying is that all the other scientists immediately, the experimental scientists immediately jumped on that to see if that was true or not. Because if it was true, it was in fact a revolution.
So their focus was broken symmetry, or,
Yes.
or asymmetrical systems.
That's right. And so Wu and her colleagues very quickly proved that it was real, experimentally. And they did that in February 1957. This is how fast a time frame this thing occurred. So we got the main work done just in 56 and early 57. By early 57, Wu has just proven it experimentally already. And the Nobel Prize Committee looked at that, and they moved with absolute incredible speed, and in December of the same year, 1957, awarded the Nobel Prize to Li and Yang. Because it did create a tremendous revolution in all of physics. In the nearly half a century since then, it hasn't migrated from the physics department over to the electrical engineering department and got them to change their model.
Give us the simplest explanation you can of how they demonstrated broken symmetry and how they defined it.
Well, their experiments were pretty complex because they were dealing with nuclear particle physics, you see. And so they did particle physics experiments, very intricate, but ones where you had equipment and techniques already worked out to measure exactly what was going on. And the measurements showed very clearly it's broken symmetry. And by the way, what's of interest to such great interest to electromagnetics and electrical engineering, one of the primary broken symmetries of nature is a dipole. Just separate a positive and a negative charge and just hold them there, leave them, just park them. You know, nail them down and leave them alone. Don't bother them. And they will radiate energy they take from the vacuum, convert it, and radiate real, honest-to-God electromagnetic energy from now till the end of time, or until you allow them to be destroyed. If you will just make a dipolarity and let it alone and not destroy it, it will take energy from the vacuum from now on and radiate it forever. That's where Heaviside's component was coming from. Once we had a dipolar generator, it's not what I'm putting in the shaft. It has anything to do with that. It's what that dipole is receiving from the vacuum and pouring out. And what it means is it's receiving one heck of a lot and pouring out a heck of a lot more than is in any of our electrical engineering books.
What's an example of an undisturbed dipole?
A permanent magnet.
Okay.
Magnetic charge is what we call a pole. And so a permanent magnet sits there and it pours out photons all the time that continually replenish its magnetic field that's traveling all the time outside there. It's not a static field at all. That's false. Rigorously, it's a non-equilibrium system, steady state. It's receiving the energy from the vacuum at a steady rate, transforming it to real energy at a steady rate, pouring it out at a steady rate. At any one point, I'll use Van Flanderen's analogy because it's beautiful. It's like a waterfall, a perfect waterfall. Every molecule of water is moving on, but it's always replaced by a molecule coming along behind. So overall, the waterfall would appear static, a beautiful form. It's not. It's completely dynamic. Every part's in motion. The same thing is true with a field. The overall field may appear static, but every photon in it is in motion at the speed of light all the time.
So a permanent magnet will stay in a dipole state indefinitely.
That's correct.
How about the battery that you buy from the supermarket?
Sure. If you didn't come back in and kick it in the rear with and fight your back EMF across it and send that current back through the battery the wrong way and knock the dipole apart, it would last far longer until, you know, something actually corroded.
But just sitting the battery there on the table.
It's
right?
radiating energy all the time. But the energy you see, you're not collecting it, you're not wiring it into a load, and the only way we've been taught to collect it is let it to flow, go in the circuit, and the circuit start using half of that collected energy to destroy the battery dipolarity. That's giving it the energy from the vacuum. The other half gets lost in the circuit's losses, and then you use it in the load. So I get less in the load that I'm using to destroy my battery. And by the way, if you use negative energy, you can charge batteries with enormous rates. For example, take the number 300 kilowatt peak power pulse. If you strike a common lead acid storage battery, say a 12-volt battery, with 300 kilowatts peak power pulse, you will explode that battery violently and blow the back end of your laboratory out with positive energy. If you strike that same battery with 300 kilowatts peak power pulse of negative energy, the battery loves it. You may get rid of some sulfation and restore a lot of the battery that's been corroded and so forth, but the battery loves it and charges just tremendously. You have no risk of explosion or anything like that. So negative energy does have some advantages. It's not trying to explode everything outward. It's trying to converge it in. Things will stand a lot more compression than they will explosion. So negative energy has lots of nice beneficial uses. One of it is it also cools rather than heats. Explosive stuff heats, convergent stuff cools. So the future is going to be involved in the use of negative energy, the use of the Heaviside component we've ignored for over 100 years and we can prove is real, and in negative energy engineering, which is negative entropy engineering. We don't have to heat up the whole biosphere and heat the rivers and all with our exhaust river flows and all. We don't have to do that all to get the energy from the vacuum. We have to do that if we use the present engineering and science we are applying. If we change the science to what's available and develop it, we do not have to do that. We can take all the energy we want from any point in the universe. Every battery sitting on the shelf, 12-volt battery, and every generator sitting in the plant already produces enough energy, if you count the Heaviside component, to power the United States. We just haven't bothered to learn how to use it. We keep throwing that big component away and pretending it's not there.
If somebody came to you, if the academic ruler of the world came to you and said, okay, Tom, we're ready. We want to start putting this into practice. We want to start going down this road.
Fine. Let him set up some funding programs and let him set up some grad students. We have some sharp PhDs who would work this area.
On a practical level, what would be the step-by-step process that you would recommend? Not the infrastructural aspect of funding and all that, the organizational part, but practically, what should people start looking towards or looking at? What kinds of experiments? Coils, semiconductors, magnetics. You know, where should people start looking to really?
Well, you see, you have me at a disadvantage now because I'm an inventor and I work with inventors and I work under non-disclosure agreements. So I can't sit here and tell you what Bearden does in his circuits. All I can do is tell you he does it, and he's filed a patent application on it. But it is working on the bench. Now, there's two ways that technology gets born. There's a conventional wisdom way that says you first go through all the scientific community and you do this and you do that, and gradually over a period of time you finally develop it and there you are. Some is done that way. Most is not. Most of it is done because some crazy fellow sitting somewhere that's wired up different in his neurons or something is noticing some effects on the bench in front of him, and he keeps picking, and he keeps playing, and he keeps adjusting until he finally finds an effect that's giving him something he really could use. That's called inventing. And most of this has been discoveries made, the original discoveries were made this way. Then the theorists come along and see these effects which don't fit the textbook. The theorist comes along and says, boy, that's interesting. And I'm looking for something that's not already old hat. I need something new to look at to try to explain. And once the theorists get in, when you get enough of them in there, you'll finally get the right fellow that can figure out how it's working. And at that point, you now have a theoretical model that describes it accurately enough, and you have some working experiments that show the effect is really there. And now you have the beginning of developing a science. You've got to reach that point. I must have the experiments that show something, and I must also have had enough theoretical work done to have a pretty good model, at least a reasonably accurate model to describe it and understand it. Then we can do science from here on. We can develop technology, we can develop science, we can develop instruments to measure all kinds of stuff. We can't do that until we understand something about the behavior pretty well, and until we have some effects that are actually working that we can replicate and show it's doing. Today's particle physics and higher group symmetry, electrodynamics, and things like that have come along far enough that today there is enough physics to put together the model. But it's in bits and pieces in all the parts of physics. It's not put together as a comprehensive model. This is a job that has to be done. Within my own personal limitations, what I've been doing is gathering the bits and pieces and trying to put them together into something that shows the whole, with the idea that then the theoreticians can come along, the real heavy horsepower, or what we call heavy hitter theorists can come along and put the whole thing together, and we'll finally have a theory that applies to taking the energy directly from the vacuum in all its aspects and using it. We'll have development of instruments which do the measurement. You know how hard it is to measure negative energy? A little bit difficult. And so solid state stuff really doesn't like negative energy. It prefers that that's already interacted with matter and produced positrons. It doesn't want to see holes. It wants to see positrons.
The measuring devices.
The measuring devices do. So they are not equipped to deal with actual holes that have not yet formed positrons or resulted in positrons. So there are many things that the inventor, for example, is struggling with. And what he does is he works out certain procedures that he finds works. Because all he's got is his discovery. Once he makes enough discoveries to where he can file a patent on this area, he has to file a patent before he has any rights at all, anything of any commercial value. He doesn't have anything worth 1 cent until he files the patent. Now, let's reason together. I'm a writer, and if I write something and it's copyrighted, the copyright is good for my life plus 50 or 75 years or something like that, and every once in a while they change it even more, you know, to make it more lucrative to me. If I'm an inventor and I file the patent on my intellectual discovery and property, I'm doing good to get 20 years out of it. When I get through fighting it through the patent office and all, maybe I'll get 18 years out of it. And that's it. At that point, anybody in the world can take it and build it, and I have no royalties or anything. So the inventor has a real problem. He's fighting the problem where he has to get to the patent stage. He has to file the patent. Hopefully he's got to fight now until he gets the patent. And then he has got to turn around and he's got to go seek venture capital funding. Because he didn't have any funding. His problem is, how can I do that? If he has been very, very successful and he's got this thing already developed to a real big system ready to go and, you know, eye-opening flashing lights and everything all over, in other words, he's done all the development work somehow, he can do it by licensing. If he has not gotten to that stage, he can do it 2 ways. He can do it the way where he finds an independent capitalist who will fund it, venture capitalist, usually taking a tremendous chunk of it, and usually taking over total control of it, and there can be disaster, because they'll put normal engineers in charge of it if you're not careful. Or he can also form his own company and sell stock in a company and things like that. That is both an advantage and a disadvantage. The advantage is it is legal to, if you don't overstate what you have and you state that you're in development on this, it is legal to sell stock and this kind of thing. On the other hand, that provides a wonderful opportunity for guys who are really con artists, who really don't care whether they got something that works as long as they got something they can fool you with, and as long as they can keep getting money from naive investors.
Well, if you're working with technology that doesn't have a worked out set of proofs, it makes it very easy to be a
That's correct. That's absolutely correct.
Nobody's got any backdrop to say yay or nay.
That's correct. So we're in an area now where the orthodox scientific community, because of its long experience with symmetrically regauged systems, is going to tell you this is impossible. They've never thought that any electrical power system takes any of its energy from the vacuum. They have no idea of that at all. Takes it from the shaft horsepower you're putting in, which is totally false. Nonetheless, that's the accepted answer. So their answer from the official established scientific community is you cannot do that. But that's always been the answer of the scientific community, anything highly innovative. Just look at history. So the problem we have is, how do we now, with the way science is now controlled, in the old days, the PhDs had some control over how they spent their research funds. They don't anymore. And they're under much more pressure to publish or perish and to get extra money coming in. They've been turned into a money-grubbing operation, not pure scientific endeavor. Postdocs are caught to say, well, most postdocs wander around after that trying to find a career and where to work and all, and many of them, half of them never find a real solid, steady working place. They just drift from here to drift to there. We don't use our scientists very well at all under this new system where we already package everything and nobody's allowed to do any innovation. But it's good for control, and it's good for the folks that are up on top because they ruthlessly control any innovation that would reduce their position or their influence. So we have a human situation which is tightened up to control and keep this kind of thing completely out of science. Because they control the PhDs, they control the research they're allowed to do, the packages they have to bid on, and they control what programs those young graduate students can work on for their doctorates and what they can work on for their postdoctoral programs. So they've got it locked up in a box. Okay, we go back to the inventor side then. Since we got a locked up scientific community until we blast it open from the inventor side, the inventor's got the problem that now he's got the whole, it's not like I have a better gadget. There's a gadget already known and I have an improvement on this gadget that you could understand the commercial value of. Now I have a system which the entire scientific community tells you is false. This cannot be done. They tell you this inventor is either a charlatan or else he's just commonly mistaken. They will give you that benefit of the doubt. But there's no room for anything else in their textbook. So the problem is, how do we now restore innovation when we got a real good system at shutting it out? Everybody uses that buzzword. Everybody talks about thinking out of the box. But when the funding comes down, they don't want to fund it. We have somehow got to pop loose a part of the scientific community, its funding and everything else, which is charged with a motto that thou shalt never work on anything ordinary. Until we have an agency and a group who's charged with doing that, we cannot do innovative science. We've got to do one more thing. The inventor says, well, we've got all these laboratories, we've got all the national labs, we've got all this stuff, I'll try to work with one of them. That's the kiss of death. These fellows in the lab, if they write a paper, they cannot copyright it because they spent government, U.S. taxpayer dollars and U.S. taxpayer time to do that. It's already been paid for. It's in the open domain. But they are allowed to file patents. That is a serious mistake. The inventor is the stupidest person on this planet if he goes to a government agency trying to work with them. because he's working with people who are his fierce competitors. They're looking for patents. Their prestige, their power, and everything depends on how many patents they can get, for one thing. So what they're going to do, if they learn what he's doing, they're going to change a few coils or something, and they're going to patent it, and you're going to have a tremendous Donnybrook. Yeah, you can sue them till you're blue in the face. If you've got a big company behind you and lots of financial power, you might win something. The odds are you won't win anything. Or you go to DARPA. A DARPA contract usually will have a nice little clause in it, particularly for inventors. It's called the government reserves march-in rights. What the devil is march-in rights? It's this. One bureaucrat writes one document that states, you are not getting, they funded the thing, you are not getting this thing to market fast enough to meet the government's needs. So the government exercises its march-in rights. It seizes your patent. It takes the whole program away from you, lock, stock, and barrel, takes it over to its favorite big contractor and has them put it out on the market and everything, and you're sitting out on the coal. Now, in theory, quote, unquote, if you sue them long enough, maybe you could get some compensation somewhere. Good luck, Charlie Brown. What you will find is you just lost your whole invention. So any inventor who knows this ball of wax is waiting on us out there is not going to do anything with the U.S. government. He's foolish if he does, under the situation at present. Now, if we would change that, where these cats can't do patents just like they can't do copyrights, then we would have something like a more fair shake. We would also have a great deal more innovation in our great national labs than we have right now, where everybody's struggling, in many cases, to be the big monkey. We've got to break that game up and get back to science and doing science, and that means innovative science. That means looking at what Heaviside found and what Lorenz then had us hide again, and go after that bit of energy that's free for the taking in everything we're producing anywhere.
This thing that you were mentioning about trying that your objective is trying to put together sort of a synthesis of all of this information. You're not really trying to reinvent the wheel or come up with a new theory of special general relativity. You're just trying to reassemble, really, or complete assembling these components that are functional and practical and exist.
That's correct. What I do is I have been going for many years, starting back before we even had good computers or anything, and what I was having to do was go through the shelves and look, hour after hour after hour at the old journals way back. What I've been trying to do is find a few nuggets that allow you to put together from these nuggets already been discovered, already sitting on the shelf, nobody's ever done anything with, and put that together and see what now comes out of it when you have all this stuff that's been ignored. When you do, you start to see energy from the vacuum, things like this, things we could do if we really put centralized and heavy programs on it and good sharp people and good funding. There really are things sitting on the shelf that have been totally ignored, and not a thing has been done with it that we should have paid attention to a long time ago. So what I've been doing is collecting these pieces, the bits and pieces, to try to put them together as something resembling a whole and say, if we put these together properly, we do have a legitimate theory and can have a legitimate science of taking energy from the vacuum, and we can solve our energy crisis. Now, these other people who made these original discoveries made the discovery. I didn't build the Sweet device. Floyd Sweet did.
Right.
I didn't build Krone's original prototype of that.
Right.
Krone did, not Tom Bearden. I read about it. I tried to put the pieces together to see where they fit and what made them tick. And this is what we're trying to pass on to the young grad students, so they don't have to spend maybe 30 years just looking for the nuggets. They can take the nugget, go back, and I give them the hard reference. They can go back and look at that reference themselves and say, make up their own mind. Does this say what he says it says, or does it not? Now, if they find I've made an error and all my pencils still need erasers, like everybody else's, change that thing and correct it and go on. But don't spend 30 years of your life just looking for the bits and pieces that are already on the shelf, just nobody ever integrated. Take that and make a science with it, solve this energy crisis, and do some great good for humanity, coming right out of the scientific community.
But in addition to that, in your experience, you have the added confirmation of observation of these inventions. That's the extra physical.
Yes, I have been very fortunate in that I have been able to work with several inventors who did have widgets that worked. Now, each inventor was a unique human being, and is today, those that are still alive. Howard Johnson built a permanent magnet motor that'll power itself and turn itself. And there is, in fact, a science of how that's done. Today, it's even in the literature. If you go to Feynman's 3 volumes of physics, and you find out about the exchange force, and they visualize a rotor and a stator magnet, and you visualize assemblies of magnets put together so that just as you are attracting in, and you get to the payback time on the other side where you start to pull back, the force reverses on you, you got your back MMF. If during that period you suddenly emit a sharp pulse of exchange force, if you cause that to be triggered, you can override the back MMF and the system will drive right on through. And that system will self-rotate, and it obeys the conservation of energy law, and it obeys all the laws of physics. Violates the hell out of violates the second law of thermodynamics. Because the second law only applies to equilibrium when those forces are equal and opposite. It doesn't apply to the system when they're not.
Who wrote the second law of thermodynamics?
A whole bunch of people twisted around with it for about 100 years. And what they did is strictly for a system in equilibrium. It does not apply to systems out of equilibrium at all. Every time you apply voltage to a circuit, you break the equilibrium, you violate the second law of thermodynamics. It rigorously applies only to equilibrium systems. Check the textbook, a good one. So it also got over-involved with the whole notion of entropy. All that entropy really means is energy the system formerly had in it that it had control of to use, that it no longer has control of. The energy didn't vanish. It's still there, but the system can't control it anymore. It may be out there in the environment. It went back to the environment. Escaped, got away. But the system has no control of it any longer. That is the production of entropy. Entropy is a measure of the energy that was controlled that's now uncontrolled and loose and can't be used. That's all it is. Now, negative energy is not a mystical thing. Anytime I get more energy into the system that now is available for my use and control, that is a negative energy operation. Potentializing a circuit is a negative entropy operation. Violates the heck out of equilibrium. Violates the second law automatically because it broke equilibrium. Equilibrium is the maximum entropy condition, standard thermo. Any departure from equilibrium automatically reduces the entropy, which is a negative entropy operation. Standard thermo, not Tom Bearden. So where did everybody get the idea you can't violate the second law of thermodynamics? It's the easiest thing on earth to violate. Piece of cake. Every windmill in the world is sitting there saying, the heck with you, second law, I'm going to operate in a non-equilibrium condition. Every solar power system, every hydroelectric power system is violating the heck out of the second law of thermodynamics. All prescribed in that part of thermodynamics that does non-equilibrium systems. But it certainly doesn't apply to equilibrium systems, and it has nothing to do with creating energy out of nothing. It's simply where something put the energy in. And then the only question is, did you have to put the energy in and pay for it, or did you trick nature to give it to you for free? The beauty of the windmill is nature gave it to me for free. It didn't pay for it. Now, that doesn't mean it's all economically free. I got to pay for the windmill. I got to pay for the maintenance. I got to pay for the generator. I got to pay for the transmission lines, etc., etc. But I do not pay for the energy. It's a lie that you have to pay for energy. You don't. Anyway, you asked me for a definition of energy.
Yeah.
That's a strange thing. In force, first I'm going to quote Feynman, Nobelist Feynman, who says, we really don't know what energy is. And he also said about force several things. You look at it in his 3 volumes of physics. He said, the main characteristic of force is it has a material origin. If you don't have matter, you have no force. That is a fact. But he said also, if you think you're going to get an exact definition of force, you know, you are mistaken. You can look for it, but you're not going to find it. It's come along a little bit since he wrote that book in the 60s. Today, from the more modern, higher group symmetry electrodynamics and stuff that's being done, particularly looking towards a unified field theory, we can state that energy can be considered two things. It's like they're the same thing, but it's the two sides of a coin. You can consider energy to be nothing but curvature of space-time or twist of space-time. It doesn't have to curve, it can also have torsion. Any distortion of space-time is energy, because when that acts on mass, it produces forces which produce translations and does work. So, you know, the old idea of energy was it's whatever it is, it always has a capability to do work, to be used to do work. It isn't capability to do work because it's not capability, but it will do work if you turn it loose. So we can look at energy itself as a distortion of space-time. That's pure energy. In fact, it's a change in energy. Space-time itself is pure energy. Now, let me stop because it's important to make one statement that normally is never considered by engineers. When we write a physics model, the choice of the fundamental units we use is totally arbitrary. There's nothing magic about mass, length, time, any of that. You can make, and they have and they do use it, a perfectly consistent and logical and good physics from a single fundamental unit. Now suppose, dogs that we are and interested in energy, we choose to use the joule, the unit of energy, as the only fundamental unit we're going to use in our model. Then mass is a function of energy. Well, since Einstein and E equaled mc squared, that doesn't bother anybody anymore, particularly after nuclear weapons. Everybody understands that mass is mass energy, but they don't understand that time is energy, and there's the same energy density as mass. 1 second of time will give you one whale of a lot of spatial electromagnetic energy if you transduce it. They have no idea that length is energy.
Distance?
Just pure distance is energy. So the best way to say it is to say space-time itself is pure energy, and any change in space-time, whether it's curvature or torsion, twisting, is in fact a change in energy. We always measure changes in energy. We don't ever measure the absolute energy. If I love particle physics, and I prefer to think of the vacuum and its virtual particle fluxes and all the...
Can you go back a little bit? We never measure, we only measure the changes in
That's
energy.
correct. Measurement only measures changes. It never measures the actual thing that's there. And that, by the way, there's any number of quotations we can use from Nobel Prize winners or all kinds of people that write leading textbooks. Everybody recognizes that's nothing unusual. I haven't said a thing unusual. We never measure the potential, only change in potential. We don't know what the absolute potential is. It could be enormous, beyond human credibility. But all we can use is that change in it that's available for our use, you see. We call that voltage.
Call that voltage.
Voltage in a circuit. So energy then can be considered as a distortion of space-time, a change in energy, excuse me. Space-time is energy, the vacuum is energy. Any change in the vacuum, its flux, direction, intensity, all that sort of thing, whether it's swirling or whether it's going straight or it's going out or it's going in, all of that sort of changes is energy, changes in vacuum energy. So what we're interested in is the changes in energy, the changes in the space-time, or the changes in the vacuum. The two go together. If space-time changes, it changes the vacuum. The vacuum changes, it changes space-time, changes energy density. So relativity agrees perfectly that if you change the vacuum, you change space-time and vice versa. So our energy that we're talking about is always the difference of energy due to these changes. So we'll take our energy directly from changes in space-time or changes in the vacuum. There is no other source of energy in the universe.
Is there any such thing as static space-time?
No.
Right. There's no space-time is always dynamic.
There is no such thing as static space-time except when you use a geometric model modeling it that way. Absolutely, there is no such thing that way, because if it were static, it couldn't change.
Right, it's the definition of static is it doesn't change.
That's right.
And space-time is always.
But Van Flandern has a beautiful analogy, which is really nice. He points out this discrepancy in the use of static fields and that sort of thing by using a waterfall analogy. A truly static waterfall, as Tom Van Flandern says, would be a frozen waterfall. So no piece of it is in motion. Well, you don't see frozen waterfalls around very often. I don't think I ever saw one. But if you have, for example, a different definition where the overall form remains the same, but every part of the internal parts are all in motion through the thing and continually being replaced, it still appears static, but it's like a real waterfall. It's not frozen. It's that kind of static. And nature builds that kind of static fields and static potential. They are not static at all. Technically, from a thermodynamic viewpoint, they are non-equilibrium, steady-state systems.
Steady state, that's different.
Steady state. That waterfall is a steady-state system if it's a perfect waterfall.
Right.
Continues to do the same thing all the time as it did just before. So, anyway, this gives us an approach to come in with what we can take as a definition of energy. It's either space-time, or if I prefer the particle definition, it's a change in the flux of vacuum.
How do you define the vacuum? Is that not an old term that really should be
No.
replaced?
The vacuum is very accurately prescribed in modern physics, because try as they would, they couldn't eliminate the fact that what we think of as empty space, number one, isn't empty, and number two, it proves to you it isn't empty because it produces real effects on matter. All of the forces that they ran into, they found were being produced by virtual particle flux interacting with matter. If it's electromagnetic forces, interacting with charged matter. But all forces of nature are produced by these change in the flux of vacuum acting on matter. So when I'm in the observable world and I got a force on something out here, I have the vacuum actually acting on that matter to produce that force. There's no force there at all until that vacuum interacts on it. And the force doesn't exist in the empty vacuum without the matter. It's only when this is acting on the matter. There is a precursor to force, something more fundamental. That's the distortion of space-time, or it's a change in the virtual particle flux of vacuum. They're the same thing.
What do you mean by virtual? What is virtual?
Virtual state is in the uncertainty principle. What they found was a thing can change, and quantum mechanics came along and pretty well established this, at least by the sets of experiments they've done. There is a threshold at which things become permanent. It's called the quantum threshold. Makes what we call a quantum of change. Below that threshold, a thing can change momentarily to any extent as long as it changes fast enough to be less than a quantum. When you multiply the energy times the time that it lasts, it can only be a certain size or it becomes a part of the real world. It makes real changes, what we call observable changes. If it stays less than that length, even though it's got enormous energy but very short time, you don't see a thing. Doesn't affect anything. Next instance is exact opposite, and all over the map, so it evens out to zero. So the integral of all this mess going on in the vacuum is normally zero. It doesn't have to be, but it normally is, unless you establish some patterning in it.
Now for the average viewer, we tend to think of outer space as the vacuum. But you're also saying that the vacuum exists within our standard 3D temporal world as well.
The vacuum is everywhere. The best thing to do without forming philosophical schools and having a Donnybrook between who's going to have what belief structure and this kind of thing, the best thing to do is just accept vacuum and space-time as being identically the same thing. Both are highly active, but until they balance out on the activity normally, until there's a change in the activity, you don't create any forces on matter. And it doesn't matter, general relativity will go along with that, and so will particle physics. So the best thing to do is just say, okay, for a country boy cut at it, I can consider the particle physics active vacuum as being what space-time identically is. Now, you guys go sort out all that other nice philosophical stuff, But as far as I'm concerned, this system works when either one of those, either way I want to look at the side of that coin, I want to look at it through general relativity or particle physics, when that change in the thing that's acting on it normally without change, when it has a change that interacts on it, that produces the forces that make things go and have dynamics. That makes the real world. So as far as I'm concerned, my system can take the energy as long as it takes it. If I prefer the particle physics view, it can take it for as long as I create these changes in the vacuum, which are free. That's free gauging. If I'm general relativity, it's the same thing. I can have it for free once I make the change in the distortion in space-time. It doesn't cost me anything to make that distortion. Now, in the real world, it'll cost you a little bit for switching and timing and control. It's like a triode. You'll have to pay for a grid signal, but you can get a lot of energy controlled and shaped for a little bit of control energy. It's not a diode, it's a triode.
So a critical assumption here is the dynamics of space-time.
That's correct.
This is an area, a current area, isn't it, of research in terms of whether space-time, this whole thing about local curvature and distance curvature and all that, this is an area in which current research which would directly influence the energy from the vacuum.
Well, it's always, the business of space-time activity has always, ever since Einstein and a little bit before him, been an area of strong theoretical concern and also experimental concern. And all the experiments so far say that, you know, space-time is active. The predictions come out reasonably well. Now, there are a few untidy ends. As we know from Gödel's work, like in the year I was born, 1930, we know from Gödel's work that there's never going to be a perfect model. All our models have loopholes. They describe a certain area of nature, but they don't get it all. And there never will be a perfect model. A lot of leading scientists have made their statements on that matter, and that's true. We will never have a perfect model. But we don't have to have a perfect model. We just have to have one that's good enough for our intended use. So if we need to take energy from the vacuum, we can't use standard electromagnetics because it says the vacuum has no activity. Space-time isn't ever curved or ever distorted, it's always flat. So you can't have any energy from outside.
And that's already been proven. That's like old news.
That's correct. It's 100 years out of date. Certainly, since 1916, it's out of date from general relativity, and since at least 1930, it's out of date with Dirac's work and the other stuff in particle physics.
The same old problem of the physicists walking across the campus.
That's right. We haven't got it from the physics department, where it's compartmentalized under a different discipline, you see, particle physics. We haven't got it to be pulled out of the particle physics box and taken over to electrical engineering and force a change in electrical engineering. We are still designing the same type of old systems that we designed 100 years ago, when all that particle physics wasn't born. Now, we're doing it lots better. We've got semiconductors, for example, we didn't have back then, but we're doing this standard old closed current loop circuit. We're using the standard tired old symmetrically regauged Maxwell Heaviside equations. We're still using and assuming the same old tired material ether because it assumes force fields in empty space. And we're still using a seriously flawed model that is no longer adequate.
Well, the sad part, or the ironic part of it.
It's ironic.
That they really had that information prior
Yes.
to the new theories of relativity and particle physics, but they didn't work. They didn't choose to work with those models.
That's correct.
Those models.
In electrical engineering, your problem is to learn how to do what we already know how to do, and tomorrow maybe you can improve it a little bit. That's basically the problem. Your problem as an engineer is to apply knowledge, not really go create new knowledge. So what we have to do is we have to find an interface where we can bleed new knowledge in and change that model that they're using. That's a hard thing to do.
So the real issue,
very hard.
The real issue with energy from the vacuum at this point is an engineering challenge.
That's right.
More than a theoretical challenge.
Theoretically, it's on solid ground. Particle physics, general relativity, unified field theory, everything tells you you can get gobs of energy from the vacuum, and all the experiments show it. They're usually with little bitty things, but it's also running the big things. So you can get all the energy you want from the vacuum, but we haven't developed systems to do it because we're using a model that says you can't. And not only that, you shall not.
Don't other nations teach a more all-encompassing electrodynamics than we do?
Yes, there are much better systems of electrodynamics available, even in particle physics. You've got the Yang-Mills theory, you've got higher group symmetry theory that has special uses. The best work that was done by the Soviet Union right after World War II. And what they did, with an iron dictator at the helm named Stalin, Stalin applied a boot to all his scientists, and he said, this great breakthrough in atomic energy and atomic bombs is not the last great breakthrough, but the next one's going to be Soviet, or I'll have your heads. He told this to his entire Academy of Science. And he wasn't kidding. He was an iron dictator. And he expected from the heads of his whole scientific academy reports, periodic reports on the progress they're making on that. And if they didn't have reports of progress, if they didn't have any progress, their heads rolled.
What was he wanted them? What was his assignment?
The next breakthrough in physics. Now. I want it now, not tomorrow, as fast as it can be humanly had. So trying to save their own necks, he got their attention, so to speak. Trying to save their own necks, they said, I looked at one of those way back there when I was in technical intelligence. They set up an institute that had 5,000 PhDs in it. It had all the staff for translation and all that with that. Tremendous organization. They hauled the literature, the scientific literature of the West by shiploads to this thing. And they went through all of the journals from day one, page by page, to review, to see what had been discovered and neglected that would be of use. This is one way of reporting progress. It's an iron way, but it'll keep the dictator from sending you off to Siberia to work you to death in the next 2 years. So what happened is all these things that got parked on the shelf got pulled out. They put what they've always been, the Russians have always been the greatest nonlinear scientists in the world, and they still are today. What we would call really good scientists were the first level of filter. Their job was to look for the things that hadn't been followed up and recognize them and put them aside. Then what I like to call the super cats, the real high horsepower scientists, were reserved to do nothing but review that pile, that much more limited pile. And they did. And they recognized which ones that had a lot of potential and which ones should be worked on and corrected. And they started and corrected all these models I'm talking about. They corrected the idea that force fields exist in space. When they did, they formed a new kind of electrodynamics, which they called energetics. And of course, they had a disinformation campaign trying to trick us into what that was and was not. And we bought it line and sinker. We thought, well, electrical engineering is everything. It wasn't.
So they weren't necessarily looking for energy from the vacuum. They were
No.
looking for whatever the new breakthrough was.
They were looking for weapons. Stalin wanted weapons.
It could have been anything then.
Anything as long as it would fit weapons. And the whole effort was highly classified.
I see. He wanted.
And it's still classified. Energetics in the Soviet Union, the real energetics, not the ones that's used for the disinformation program, but the real energetics is still extraordinarily classified and is still under the direct control of what used to be called the KGB and today is called FSS. So the scientists themselves that do the weapons work with this higher group symmetry electrodynamics they came up with are still highly classified in the Soviet Union. But the point is the problems in the models are well known. Leading scientists have pointed out that you don't have force fields in the vacuum, in empty space. You can't have it. So why are we still teaching it in electrodynamics?
So on top of this, we're because of the classification issue and the weapons emphasis in the Soviet Union.
They weaponized it. They built the weapons.
But because of that, we didn't get that traditional academic sharing.
That's correct. That's
peer
correct.
review.
That's typical of any deep black program, as we would call it. We would say if we formed a deep black program, they don't share anything. Everything goes in, nothing comes out. And so it's the same way in Russia, any other place that uses that approach. When you highly classify something and compartmentalize it and so forth, you bury it to where you don't release everything that's going on in there at all.
And we do not have a similar component, never have in this area of physics even within our weapons development. We are not, we just have not, we missed the boat in our country.
We missed a lot of it. Let me comment on that question by saying we've missed a lot of it. Maybe we haven't missed all of it, but let's reason together. If it is a deeply classified program, it's not public. And so we wouldn't know about it if we had. So the question is, what do we have that's openly available to the scientific community? Openly. All they got to do is pull the book off the shelf and read it. There it is. That they could be developing openly with their own resources. They don't have to have a deep black program or anything like that. It's just a matter of modernizing something that's very, very archaic and aged. And that's the part that we're not having done in our society. Nobody is updating the old electrical engineering model.
But we do have...
Other than the book that you wrote.
Well, we're trying. I have to point out again that I've been very fortunate to work with various inventors who had working equipment, so I was able to see a good bit of phenomenology, much more so than the average person trying to study in this area would be able to see. So what I've tried to do is take everything that I've been able to pull out of the literature to support the phenomenology I actually saw, and was able finally to explain that, and try to share that, and share the references that I found, so that the young fellows starting in to try to do the job I'm saying desperately needs doing in science won't have to spend 30 years of their life doing that. They can start with all of that. Hopefully we can involve the scientific community then in making energy from the vacuum a viable science that's taught in our schools and built in equipment and used in our power systems.
Two things. First one is, do you think the Russians have any, free energy systems designed?
Question is, does the Russians have free energy systems? Yes, and several other nations and groups and all of this. There's all kind of groups that have free energy systems already working, but they're all in special installations that we are never going to see. They are working in this country, in mountains that are hollowed out, for example, in certain places. They're not necessarily under the control of the U.S. government. Don't blame the government for everything. There's a lot of folks that have a lot of activity and a lot of ulterior motive that have nothing to do with the government. So yes, they're in this country. Yes, Switzerland has some. There's some pretty strong stuff in Switzerland. There are some of the underground installations that existed in Germany during Hitler's day, we still don't know what was going on in them to this day.
Wow.
So there are developments everywhere that are not in the standard textbook we go down to university and study in quite a few nations. Not only in the weapons area, they also have some in energy area. But these are not shared with open science. They're all in a closed box.
So there's really two factors at play here academically. One is this, the practical result of this, this curtailing of the theories early in the century.
That's correct.
The other one is the limitations and isolation created by security arrangements regarding defense and weaponry and all that.
There are several factors involved. The one that you pointed out is the work that occurred early in the century and froze, so to speak, some of the engineering sciences. For example, radar engineering and so forth uses pretty well standard techniques. They have some developments, of course, new, but basically it's still radar engineering. Electrical engineering is still basically the same electrical engineering that started out about 100 years ago, really got going after Lorenz did the regauging and so forth. And particularly after Tesla's work, he gave us the rotating field so we could have practical motors and generators. So the problem is that we haven't continued to update what got pretty well locked in place 100 years ago. We haven't updated that as physics came along and found out a lot of other things in this 100 years. We're still using the same model. We're doing it the same way. We're using the same closed current loop circuit. We're wiring in the generator. We're killing the generator's dipole. We don't have to do that. There's no law of nature says you've got to use a closed current loop circuit at all. But we're still doing it the same old way we've been doing it for 100 years, which is guaranteed, absolutely will ensure you never put an over-unity system on the market. You never have one that takes any energy out of the Heaviside component. You never have one that will use all the excess energy it can take in from the vacuum if it would but receive it.
No one knows how to design it.
Nobody wants to know. This is the problem. See, in science, you have what has been built and gone and been successful. You have the problem, if you want to be successful in life, this is a human situation. It's not just all abstraction. You got real human beings, and real human beings have to develop an income, they have to develop a position, they have to develop some, hopefully, security of position. So you have many human factors involved in it, and to obey your human factors and live and do well, you're going to have to play the game. You cannot rock the boat all the time and play the game. They'll throw you out with the dishwater. So the young fellow is facing a problem where he might want to rock the boat, but he's going to be the luckiest fellow in the world if he does it very bad and get away with it. He probably won't get away with it, just get ruined. Once in a while, somebody does rock the boat and gets away with it. It usually takes about 50 years then to accept what he's done. Like Wagner. When Einstein first came out with what he did, that was considered total lunacy. I mean, he was a Swiss patent clerk. What the heck do patent clerks know about physics, right? So what we have is we have this tendency of the scientific community, once you've progressed in the application of what's already known, it's very much in your interest to not have too much deviation from that. Otherwise, you're pulling the rug right out from under your own feet. You're turning your own rice bowl over and emptying it. Want to know why we don't do research in energy from the vacuum? We empty all the big rice bowls. Nobody wants to do that. So, you know, Max Planck ironically stated, you know, you don't get a new science by sweet reason. That's not the way it happens. You get a new science when the young guys get familiarized with it, and the old guys that so adamantly oppose it finally die off and get out of the way. He said it nicer and more elegantly, but that's what he said, and he's right. Freud pointed out the same thing. The human nature resists change. And every new discovery has been total lunacy when it was first done. The second stage is, well, yeah, it's true, but it has no importance. And the third stage was, we knew it all along. There is a fourth stage. We did it. Now watch that happen. Now watch that one happen in some large national laboratories in this country. So I'm familiar with the fact we did it after the fact when they took the discovery from the Soviet Union. I won't go into details. But let me put it this way. It was a very fundamental discovery that our guys said was completely against the laws of nature. Once they built an atomic weapon cruder, the way the Russians did, instead of so elegantly the way we did, and put that in an underground test, all of a sudden this thing that was totally against the laws of nature couldn't be done. Pow! Just like that. There it was. A few months later, the national labs were taking credit for that discovery. It wasn't their discovery at all. It came directly out of Soviet Union research. But that's not the way it got represented. It got represented as our discovery. And they made it work. They took a lot of credit for that. Anyway, that also is a human trait. In human beings, we have a bell-shaped curve. Okay, if I believe the bell-shaped curve, 9% of those human beings have the utmost morality. They're tremendous people. They're the salt of the earth. They should be rewarded tomorrow. The main body is just ordinary people trying to do a different kind of job and trying to do it well. That's the main body of folks. But this other 9% on the bottom has no morality whatsoever, no ethics, will do anything, including some of them will actually kill people. They will do whatever is necessary to feather their own nest, achieve power and position, and play the big monkey game. Now, 9% of every large organization of human beings does that and nothing else. Nothing else matters. Science doesn't matter. The country doesn't matter. Nothing. Once you understand this is a human situation, I have to deal, and you have to deal, and the public has to deal with the results achieved by that 9% that's undesirable, that's struggling to take over and run things all the time. And they have been too successful, more than 9%. Fortunately, not entirely successful. But what we have is a part of science itself which suppresses innovation in science. And historians of science have pointed this out for many, many years. So all of those factors are involved when you come up with something and saying we need to be taking our energy from the vacuum. And here's the various things we have to do that. We have to develop, we have to take the discoveries that have already been made, we have to change our electrical engineering model so that it will model some of that. We have to turn these young grad students and postdocs loose so they'll do the experiments and all to work out the phenomenology for us, and replicable phenomenology, and develop the instruments that are needed to measure it, and then we'll gradually have a science and a technology that we'll start using. And we'll quit polluting the biosphere, we'll clean up the earth, we'll have cheap, clean energy, we'll do enormous good for humanity, and we'll stop having to fight wars for oil.
I'm going to change it, go back where we were a little bit ago. Can you please give me your definition or a definition of space-time?
Definition of space-time is everybody has a sense of space, which is really intervals between physical things. When you come right down to it, length is a basic definition of space. We consider length, height, and width. But we also have a sense of separation in time. We don't know what time is, but we think of it innately as if we were in a boat on a river, and there was a stream and a current going in the river, and we were floating in this boat down the river. We passed this landing, and then we passed that landing, and we passed that landing, or the river goes around and around, and we come by and we see the tree, and we see it again later, and it's changed, put out leaves. We see it again later, and from the changes that we see in things, we generate the notion of the passage of time. We really don't have a definition of time anywhere in the literature at all. So what we have different positions on what it might be. It's like philosophy. Philosophy never solved its own problems. It set up schools. It took up positions with elegant statements. Science does the same thing. It is, after all, natural philosophy. So what we have is a sense of the passage of time that we judge by the changes we see in objects around us. That's how we infer a year from seeing that we get back around the sun again, etc. We infer a day by the fact that we're back looking at the sun in the same position in the morning again. So from the changes that surround us, we infer the passage of time. Einstein put it together based on some of the geometry he was looking at and said, if we call it all geometry, then I can make it very abstract, and I can model the length in 3 directions, and I can model that fourth. It's just another length, special kind of length. Put an eye in front of it to make it imaginary. It would still exist in time, just doesn't exist in 3 space. And he made a 4-dimensional space, and that came to be called space-time. The geometry was done by different folks, but he took the tools that could be used to construct that as a theory and made his relativity theory in terms of that model. And that's where we got so interested in space-time as a geometry, a geometrical system. It's just a model. It's just a geometrical model of what we're doing.
Could you say, I mean, in the practical world, not in the theoretical model world, you cannot have 3 dimensions without the 4th dimension.
That's correct.
You must have time.
The dimensionality you apply is also up for grabs. Particle physics.
I use that word, but
Particle physics, for example, has certain models that use 11 dimensions. So there's some of them that use 20-something these days. So a dimension, in a basic kind of sense, this is not too exact, so don't crowd it too far. A dimension, in a sort of a weird sense, is just a fundamental variable, a very fundamental variable. You can move there or here. You can do that in time, right? You can be later in time, or theoretically it was earlier in time. If 2 people do something, well, he left earlier. So you can compare earlier in time. So everything we think about as a kind of a distance, because we're familiar with that in our real world from our sense experience. And so the dimensions that we set up really are just extra separations and extra variables that we can add in for more complexity in the functioning. When we do that, sometimes we see functioning that turns out to be physical out here that we couldn't see otherwise.
So time is a form of length, form of
Yes,
I'm sorry, distance.
in relativity, you can turn distance into time, you can turn time into distance. You have time dilation, a second gets longer. It doesn't die away as quickly. When you have enough velocity, your length gets shorter, your time gets longer. Called, time dilation and length contraction. So in the way you model it, this is the way it comes out. When you reach the speed of light, there's nothing magic about the speed of light, is that along your line of propagation, your length shrunk to zero, and now you just, at best, a flat plane moving at the speed of light. So the photon is not three-dimensional, the way we would model it in that kind of model, space-time.
So space-time is, for the average person, is really the joining of space and time.
That's correct in the common geometry, but you see, joining it means you can take time and turn it into length, or you can take length and turn it into time. It's even worse than that. We can replace all of that with just energy as a single fundamental unit. We can turn time into energy, we can turn length into energy, and all of that stuff. Eventually, I think, energy from the vacuum will have to do, the scientists, when they really want to get into real large amounts of energy, will probably wind up doing conversion from the time domain, converting time into energy. Because it's awfully easy to get enough energy out of a small system that could power the whole United States if you do that. And even if you wind up with a very inefficient process, you could power a big city. So there are many things eventually that can be done once we ever get the basic start and get towards a model and get towards a technology and get towards some things that work, and we start doing the energy that we need so desperately. Get off of the oil and the coal and all of that, or at least total dependence on it. Reduce that dependence.
Well, where the hand is getting forced now. It's getting to where historically we don't have much choice but to start introducing something.
That's correct. Yeah. The first thing you will have happen when things start getting scarce, because of human nature, the monkeys start fighting over the bananas, right? When there's a limited number of bananas. And the big powerful monkeys start getting the bananas, and then they become powerful by which monkey they choose to favor with giving a banana or a bite of banana. So humans play the same game, and so what we will get into as energy gets shorter and shorter, we will get into the big monkey games. That'll include wars and everything you ever heard of, terrorism, you name it. All kind of isms get turned on. But the thing is, you first struggle over control of what's there to be had. That's the primate dominance thing. You've got to become dominant over there, what's available. Whether it's territory, when people used to fight for territory, or whatever. Fight for a system. I want my system to be over you and over everybody else, or else I want to get rid of you. It was, again, a fight for dominance, you see. And the same thing is true when energy becomes a tremendously critical thing and it starts really strangling people and strangling nations. It becomes a matter of national dominance at that point, survival. They will call it national survival. But what we will have is it spawns all of these human struggles. This is just the nature of the human being. And there's no way to avoid that, unless you go from the point where you don't have nearly enough and you have the big monkey game going in the struggle. You go to where you have all you wish and anybody can have it, and here, take some bananas. We got trees full, we got plantations full, have some bananas. At that point, the monkey game goes away.
Yeah.
But as long as you've got scarcity of the bananas, you'll have the big monkey game. And right now, energy-wise, we're getting scarcer of bananas every year. Now, this country, we have one fallback. We have lots of coal. If you scrunch us too hard, you will see more coal burning. That's why there's over 100 coal-burning power plants on the drawing board right now to build. There's only 2 nuclear power plants that they're trying to get permission to build again. But they got over 100 coal-burning plants that they're going to build. You have to. That's the only thing you're going to be able to dependably have a supply of resources to burn.
That's
to
like
produce
going back
energy.
to the 19th century.
That's correct. Because the process we're using to produce the energy for the customer is the 19th century process.
Yeah, exactly.
We're way back in the dark ages still with our process. So we really need to modernize the process.
Yeah.
with what is already in the physics book. It just hadn't been taken over to electrical engineering, hadn't been wired in. We haven't spent the time and the dollars to turn the young postgrads loose and the young guys working on their doctoral theses, and turn some of those sharp professors loose that would work on this if you wouldn't ruin their careers or wouldn't destroy them. Turn them loose and let them do something that will benefit the country and benefit all of mankind. And benefit science as well.
Forever.
Forever, that's correct. This will be a permanent benefit.